All right, so we're going to work through a bolted joint problem. This is problem example 8.2 in your textbook, chapter 8, example 2. A through bolted joint. Let's draw this puppy out. We do have a couple of material constants that sit in there. There's going to be a joint between a steel plate and an iron plate with, of course, a steel bolt and washer. So the problem as drawn. There's our bolt going through the middle. Have a 1/2 inch thick plate of steel. We have a 3/4 inch thick, not to scale, not to scale at all, piece of iron. Okay. And then we have our bolt going through all of that. There's a nut on this side, the washer here, some size, and there's the head of the bolt on top of that. So the nut, the washer, that's the head of the bolt. This thing, of course, is threaded some length. This is a bolt used. This is a 1/2 20 bolt. A 1/2 inch long, 1.5 inch long, and the washer is a 1/2 N washer. So this means that's a washer for a 1/2 inch bolt and happens to be narrow. We can flip to the back of the book. We're in table A31. A31 gets us the nuts. A32 gets us the washer. Look back over in here, have my table of fastener sizes and washers. So go down to 1/2 N, the 1/2 inch washer with a 1.062 inch OD. 1.062 inches on the OD. I'm going to write down everything so I have it. 0.531 inch ID, and the thickness I'll call it lowercase e sub w. That is 0.095 inches. Great. While I'm here, I can turn back one to table A30. Table A30 has the dimensions of hexagonal cap screws. Nope, I want table A31. That's dimensions of my hexagonal nut. For a 1/2 inch nut, a 1/2 inch nut, it's on a 1/2 inch bolt. It has a width, draw a hexagon, has a width of 3/4 inch. And it has a height for a regular nut of 7/16 of an inch. Great. Last thing I'm going to want to grab is dimensions of my bolt. So now I'm in table A29. The washer was A32. Nut was an A31. Bolt dimensions A29. So for a 1/2 inch bolt, half-inch bolt, a regular hexagonal bolt has a width of 3/4 inch, same as the nut, conveniently. Regular hexagonal, just a note. And might as well grab the height while I'm here in case I need it. Height is 11/32. Great. Okay, so that should be all the information that I need. So where to from here? So first question is, what's putting this joint into compression? So you have this bolt, you have the nut on one side, you have the head on the other. If I think of this joint as I slide the bolt into the joint's still not in compression, but it's being held on one side by the head of the bolt, right? When I put the nut on, it starts to squeeze everything together, squeezing all the material in the grip, that's everything here, the steel, iron, the washer, between the nut and the head. So the nut and the head are where everything's in compression. And we said that based on that, we model the stress distribution in the grip as this pair of cones that go out from where the compressive load's being applied. So we have some compressive load from the nut and from the head, comes out at a 30-degree angle from each side. And make this somewhat symmetric. So that's how the stress is being distributed inside the grip. We need to find out some stiffness based on the stress distribution so that we can figure out what the load is on all of these members and make sure that we preload it correctly so that it has the mechanical properties that we desire. So the trick is, though, when we evaluate the stiffness of the grip by these frustums, by these conical sections, if you will, the equations that we have set up only can do one cone at a time, if you will, and only one material at a time. So what we need to do is kind of divide this up. If this joint was symmetric, I mean perfectly symmetric, there would be no washer, these materials would be exactly the same length, it was perfectly symmetric, then these two cones would meet right at the intersection between the two materials. And if the materials were the same, this would be really easy. But I don't have to do one computation. I know that it would be the exact same thing for both the top and the bottom member. However, that's not what we have here. We have two different materials, including the washer. The washer we say is made out of steel, and most steels have relatively similar elastic moduli. So we're saying the washer and the steel layer are pretty much the same material. So we're going to use the same elastic moduli for both of them. But we have two different materials here, steel and iron. And also the joint is not symmetric. So we can't assume that the cone emanating from the head and the cone emanating from the nut, in other words, the stress being produced by the head and the stress being produced by the nut, we can't assume that those stress distributions meet at exactly the center of the grip or exactly some convenient place. We have to figure it out. Before we do that, let's just set this up a little bit more. Based on where that meeting point is, it's probably not going to be this interface line here between the steel and the iron. It's probably going to be some point inside of either the iron bit or the steel bit. My bet's on the iron bit. Based on where the intersection point is, that's going to divide this stress distribution up into multiple parts, multiple frusta, meaning multiple cones, that we're going to have to compute the stiffness of separately and then combine. So if the point is indeed where I think it's going to be, somewhere in the iron, then I can think of this bottom half as one frusta, so it's going to have its own stiffness, because I know that based on the way that we derive the expression for stiffness, I can compute the stiffness of a cone going out as soon as it makes a turn, like around this point, or changes material. I have to do a new computation, so I can compute the stiffness of this bottom part. And then I'm also going to have to compute the stiffness of this bit here, not because the direction of the cone changes this time, though. It's because the material is going to change as soon as I leave the iron. So that's going to be another stiffness I'm going to have to compute. Call that K2. Then I can compute the stiffness of this steel region here. Call it K3. And then I'm also going to have to compute the stiffness contributed by the bit of washer that gets involved. Call that K4. So those are the 4 stiffness computations that I'm going to have to run. So that's what we should be expecting. Then once we can compute those, these are all springs in series. These are all stiffnesses in series with one another, right? They're lined up. So I can compute the stiffness of the joint, or stiffness of everything that's in the grip, by adding their reciprocals and taking the reciprocal of that. Okay, so that's my game plan. So where do we start? Well, first thing is I have to figure out where that intersection point is between the cone of pressure, cone of stress, the stress distribution, whatever you want to call it, coming from the head and coming from the nut. I have to figure out where those two intersect. Well, what I do know is that those two will intersect at a point that is halfway between where they start, quote unquote. Because I know that there comes down at a 30-degree angle, goes up at a 30-degree angle. If I can figure out kind of a common point that they start from, then where they meet should be halfway between the two. This should be an isosceles triangle. So if I can trace this 30-degree line back to the edge of the hole, and then going along that same line, find where the other her stress distribution comes back and hits on that same edge. I can find that and find the distance between those 2 points, call it D. This point here would be at a location 1/2 that distance from either end point. So this end point may or may not be in space or in a piece of material. It really doesn't matter. It's just a geometric reference point. But these are the points that I have to find first. So get a fresh sheet of paper and get to it. All right. So just redraw my thing quick so we got it. Okay. So there's our iron layer. There's steel layer. This one's 3/4 inch thick. 1/2 inch thick. Now I have a washer sitting on top of that, which is another 0.095, yeah, 95 inches thick. I know that my stress distribution starts at a point that is a measure to the center of this hole, it's 3/8 of an inch from the center of the hole, because the whole head of the bolt is 3/4 of an inch wide, so half of that 3/8. This hole, well, it's nominally a ½ inch, right? Because that's how big the bolt is. If I go to a tap and drill chart, I'll likely find that it's slightly larger than that because the bolt needs some clearance. So if I look up tap and drill chart, here we go. Tap and drill chart for a ½ inch bolt, clearance is 0.5156. So the diameter of this hole is 0.5156 inches, means that the radius would be 0.5156 over 2. So this radius is 0.257. Great. All right. We got that. Got those two. We know that the nut sits about right there, and it is also 3/8 inches from the center of the hole. All right. So what I want to do is, as said, I want to find where this point of intersection is between the two stress distributions. And in order to do that, I have to take this line back to some common point. And conveniently, this hole is the same diameter the whole way through the material. So what I'm going to do is I'm going to trace the stress distribution back to the edge of the hole on each side. Okay. So I know that I'm sitting here about 3/8 inches away from the side of the hole. Actually, that on the top and on the bottom. I know that this is a 30-degree angle between the vertical and the stress distribution line. So if I know this width, I know my angle. Well, I call this y. Tangent of 30 degrees for this little triangle here would be 3/8 of an inch over y. So y equals 3/8 inch over tan 30, which put it into here, see 0.375, 30 degrees, tangent of that side, that gets me 0.6495 inches. Awesome. So I know that that's 0.6495 inches top and bottom, because that's the same triangle here. It's moving over. Oh shoot, I did that wrong. Sorry. Not 3/8 of an inch. So 3/8 of an inch minus 0.25778, because you're not going to the center of the hole, you're going to the edge of the hole. So 3/8 inch minus 0.2578 inches. Uh, 375, 578 minus. That gets me 0.1172 inches. That's my actual distance from the edge of the nut to the side of the hole, from the edge of the bolt to the side of the hole. So that divided by tangent of 30. There we go. That's 0.2030 inches. Much better. If you ever have questions about your geometry, if you're doing it right, one easy way to check it is just go into CAD, draw this up, draw your 30-degree lines and see where they come out. So you just use some geometric constraints and check everything pretty straightforwardly. Okay, so I know that this line to get to the edge of the hole comes down another 0.203 inches. That's true top as well as the bottom because it's traversing the same difference in length. Okay, so now I just need to add up all my lengths along here. So I'm going to say 0.2030 inches. That gets me from this point here to the start of the iron. Gets me from there to there. Then I add in the thickness of the iron, so that's 3/4 inch, is to get the total length from here to here. Add thickness of the steel, add thickness of the washer, and then add this little last bit up to there. And this, from our last sketch, will be D, total length, and then D over 2 will be the distance from the point that I just computed, the one that's sitting on the edge of the hole in parallel with my stress distribution, to where those two stress distributions from the head and the nut meet in the part. So let me just store this guy quick. And I remember how to do it. There it is. 202. There we go. That's cool. That's just stored in my calculator memory somewhere. I need to keep track of it. Okay, so I have 202 plus 3/4 plus ½ inch plus 0.095 plus another 0.2030. Add all those up, I get 1.751 inches. Store that my calculator memory. Great. And then D over 2 is 0.875 inches. So that means 0.875 up from here is where the two stress distributions will intersect. So if I go up from my starting point, so I'm going to subtract 0.203 out of it, so that'll get me kind of the distance from the edge of the iron plate to my point. It says that point is 0.6725 into my iron plate. And since 672 is less than 3/4 of an inch, I know that it's in my iron plate. So that's where the two stress distributions will meet. It means that this length here, the length of the second frustum that I have to compute in the iron, this guy here, I labeled it K2. This guy here, the thickness of that is 0.75 minus 672, 0.0775. Cool. So I should have all my dimensions here. Let's see, the only thing I might need, I know that as I go through my equation, let's just apply it and see how things go. So I'm going to start from the bottom and see where things go. So now that I have all the locations along here that I need to compute at, I'm going to start crunching away with the stiffness equations and see where things go. So I'm going to start from here. I'm going to compute K1 first. And for reference, K1 would be the stiffness of this bottom frustum here. All right, so if I look at the general form of the equation for member stiffness, where it is K1 equals pi times the elastic modulus of the section, d times alpha over natural log of 2t and alpha plus cap d minus lowercase d, all that multiplied by cap d plus small d over 2t and alpha plus cap d plus small d times cap d minus small d. Great. So that's the general form of my equation for stiffness. If you look in the textbook, right here on page 428, figure 8.15, we draw the figure here. When I'm looking at my frustum, generally the frustum looks like that. So this is the stress distribution. It's kind of the cone that I've chopped out of my grip, if you will. There's the hole that is in the middle of the grip, the thing where the bolt goes through, and that's lowercase case d. So that's our clearance hole. That's 0.5156 diameter hole that the bolt's dropping through. That's our small d. Then we have the diameter of the top of the frustum, or the top is a misnomer. It's really just the smaller end of the frustum. That's cap d. That's one that we're going to have to be very careful of as we go through here. And we also have it in terms of the thickness, t, and the angle, alpha. Well, we already said that that's 30 degrees, so that's pretty straightforward. We just have to figure out what big D is. Small d, we know, is always the clearance hole size, because our hole is the same diameter the entire way through. Very key to note. That will not be true of a tapped hole. For us, however, it's nice and straightforward. Write that out. And t is also going to change, although we just computed all of our t's, so we just have to make sure that we grab the right one. Really, the thing that we're going to have to compute as we go is cap d. All right, so for K1, the small end of our frustum is on the bottom. It's not the nut. You know, the nut is 3/4 of an inch wide, so that's our cap d for K1. So for K1, equals pi times, see this, the nut, so it's made out of steel. So that's, I'm sorry, starts with the nut, goes through iron. So the elastic modulus of iron is 14.5 times 10 to the 6th psi. Small d is our clearance hole size, so that's 0.5156 inches times tangent of 30 degrees. Our numerator, oops, there we go, divide by natural log of. Okay, so this first frustum, this is that one here, extends up 0.6725 inches. That's where the intersection point is that we computed before. So that's as far as we can compute here. So it goes up to there, 2 times 0.725 inches. That's our t. It's tan 30 degrees plus, we said cap d was the diameter of the nut, so that's the small end here, small end of the cone here, so that's 3/8 of an inch in diameter. That's 375 inches minus 0.5156 inches times these fractions, so they're smaller. 515 inches. Great. Divided by 2 times 0.6725 inches. Tangent of 30 degrees plus 3/8 inch plus 0.5156 inches. 3/8 inch minus 0.5156. Oh, sorry. It should be 3/4. My apologies. All the 3/8 are really 3/4 because it's diameters, not radii. There we go. This number you should never end up with a negative number here. So if you do, you've probably used a radius instead of a diameter. All right. So if we crunch all that, remember our units are pounds and inches, so we should expect the units of our answer to be pounds per inch. So pi 14.5 times 10 to the 6, 0.5156, and 30. That's into numerator. That, store that into memory 3, and then 2.6725, 725, mention the 30, 3/4 inch, add that, 0.5156, subtract that, 0.75, 0.556, add those. Okay. Top of this is 1.2794. Now 2.6725 times the 30 times 75 plus 0.5156 plus 0.75, 5156, subtract those, multiply that, put the denominator, 0.4787, divide those two, natural log of 2.672, two, 794 over 787, get that to be 0.983. Okay, so then I take my numerator of 13,560,000, divide that by 0.9, I get that K1 is approximately 13 million, or 13.793 times 10 to the 6th pounds per inch. That's K1. Great. Now for K2. Or rather, if I look at this again, well, K1 was the easy one, because I knew where I was starting from, knew where I was ending from. K3, I know where I'm starting from vertically, I just don't know where it is horizontally. So let's start up here on K4. Compute this little frustum in the washer. So for that one, just follow the same method, except now it's the washer's thickness, which is 0.095. So I'm just going to write out the equation again for reference. So I'm going to leave you to do the substitutions. It's the same equation every time. You just have to figure out what to put in, pretty much. All right, there we go. So this is the washer. We know that the clearance hole size is always the same. So small d, so 0.5156 inches. That's the interior size. That's that hole still. Where the cone starts from. Well, we're going through the washer, starting from the head of the bolt there. So know that that's a 3/4 inch diameter. That's that. And the thickness is just how far it's going. Well, we don't necessarily change material here. But technically, I could just compute this entire frustum here in one shot. And so they're just computing it for K4 because both this piece of steel here and the washer are the same material. Technically, I could do that. You know what? We actually don't lose anything by doing that. Yeah, we're just going to do it. We're going to compute this whole thing as one because it's the exact same material the entire way through. So K4, I'm just going to ignore that. I'm just going to compute K2 as this entire region here because it's all one material. So this means that my thickness is from the interface between the iron and the steel to the top here. So that's 0.095. That's the thickness of the washer. Plus a ½ inch thickness of the steel. Or 0.595 inches. Great. So I can stick all those in. Keep in mind that E steel, the mass modulus of steel is 30 MSI, or 30 times 10 to the 6 PSI. Okay, so pi 3 times 10 to the 6th, 0.5156, tangent of 30, for that in memory 1. Okay, next line, 2 times thickness, 0.595, tangent of 30 degrees, multiply all those, 3/4 inch, add those, 0.5156, subtract that off, 5156 plus 3/4 inch, multiply those, okay, get the numerator to be 1.166. That was the same as the last, well, would be the same as the last one. Can store that off into memory 2. Okay. Just make note of where my numbers are in my calculated memory. Next one, 595 times tangent of 30 times 0.75 plus 0.5156 plus 0.75. Track those, multiply that. My denominator be 0.457 in my denominator, or 77. Call divide 1.166 by 0.457, natural log of that, get 0.935. Take my 28 million from the numerator, divide those, and I get my K3 or K4, whatever you're calling it, the stiffness of all my steel at the top, be 29.997 times 10 to the 6th pounds per inch. Okay, so that gives me this guy up here. Now I just have to figure out the stiffness of this region here, which means I have to figure out where that point is so that I can get, that's a small part of my frustum. So if I can get where that is, I get D, right? So I know that I started at a radius of 3/8 of an inch out from this point. Then I went down 0.595 inches to get from here to here. So in theory, I should just be able to say tangent to 30 times this distance gets me this leg here. So tangent to 30 times 0.595 So I moved out 0.34 inches, this distance here, 0.334. So 0.34 inches plus 3/8. If I multiply that by 2, that means that the diameter right here at the interface, the diameter of the stress distribution at the interface is 1.437 inches approximately. So when I got my last stiffness, I'm going to call it K2. The same equation is up there, so I'm not going to write it here again. Small d is still the same because that's the size of the clearance hole. My big D now, however, said is the diameter of the frustum additional way down here now. So that I just computed to be 1.437 inches. And again, I just did that by saying that I have this triangle here. It started at the head of the bolt in this case. It went down to this point of intersection here where my next frustum started. I know that this angle is 30 degrees. I know how long this leg is, so I can find how long this side of the triangle is. Then I can add that radius onto this radius, or the distance from the edge of my bolt head to the center of the hole, and find out the radius of that point, the point where my frustum starts, and I can multiply that by 2, and that gets me 1.437 inches. Thickness I had figured out before. I go over here, found out where the point of intersection was, so it's 0.0775. And this is an iron, so it's a 14.5 times 10 to the 6th psi elastic modulus. So I can crunch those numbers, get a value for K2. So pi times 14.5 times 10 to the 6th times small d 5.56 times 10 to the 30. Okay, that's my numerator, 13.56 times 10 to the 6th. And it's 2 times 0.0775, mentioned to 30. Plus 1.437 minus 0.5156. And 1.437 plus 0.5156. Multiply those. Get 1.973. So it's right now it's 13.56 times 10 to the 6th over natural log of 1.974, I guess, if I round up. And the denominator would be 2 times 0.0775. It's tangent to 30 degrees plus 1.437 plus 0.5156 and 1.437 minus 0.5156. It's 1882. So call this, flip, divide, natural log of 1.05, then divide 13 million by that. That gets me K2 approximately 283 times 283.21 if you want, times 10 to the 6th pounds per inch. All right, great. All right, so now I just have to combine all those. So I have all my stiffnesses. And say K grip equal to 1 over K1 plus 1 over K2, and then I combine K3 and K4 to one shot. So let's do that. So K grip, take the reciprocal of that. Let's see, 283 plus, let's see, 13.793 times 10 to the 6, reciprocal of that. And then where's my last one here? K1, that was K2, K3 was 29.997 times 10 to the 6. Okay, add all those, and then take the reciprocal of that. Means the stiffness of the whole grip is 9.143 times 10 to the 6 pounds per inch. And that is that.